Let's take a look at some of the basics of frequency modulation, or FM synthesis. Throughout this video, we'll be using Ableton Live's software synth operator to demonstrate FM synthesis. Before we begin, it should be noted that any deep dive into the math and theory of frequency modulation is well beyond the scope of this video. Anyone interested in the theory and math behind FM synthesis should check out some of the great textbooks and articles written about the subject matter. Frequency modulation, or FM synthesis, was explored and used compositionally by John Chowning beginning around 1970. His discoveries eventually led to the design and release of the Yamaha DX7 family of instruments, one of the most successful synthesizers of all time. Let's see and hear the difference between additive synthesis and frequency modulation synthesis. So here I've got a very simple, I've got 3 oscillators, each producing a different frequency. So oscillator A is 800 Hertz, oscillator B is 200 Hertz, oscillator C is 400 Hertz. They've all got the same envelopes. And I'm using the additive synthesis algorithm in operator. Here's what this sounds like. Notice I'm using all fixed audio rate here. I can change the character of the sound by adjusting the levels of each of the oscillators. So at its most basic, additive synthesis is a sound generation method that involves the combination or mixing of simple waveforms. Each of these oscillators is independently mixed together. Let's listen now to the same patch, the same sound, and we're going to switch it to FM synthesis. So you can see there's quite a difference in terms of the harmonic spectrum of the FM synthesis patch. If the output of an oscillator is applied to the control frequency of another oscillator, frequency modulation, or FM synthesis, will result. So let me get rid of one of these for now. We'll just work with 2 oscillators. So the oscillator providing the control source is referred to as the modulator. So that's oscillator B here. This one is modulating oscillator A. And so the oscillator providing the signal is referred to as the carrier. If the modulating oscillator is tuned below audio rate, or approximately 20 Hertz, sub-audio frequency modulation or vibrato will result. I'm going to show an LFO to show how this LFO will modulate this oscillator A. So right now I have a sine wave, and you see that as I increase the rate, it'll change the speed of the vibrato. And then the amplitude will change how much of the vibrato there will actually be. The shape of the vibrato is determined by the modulator's waveform. So right now I have a sine wave. Let's switch to a square wave. And now switch to a sawtooth going up. And a sawtooth going down. It is important at the outset of the discussion to realize that the modulator is not part of the signal path. It is never heard directly, only its effect on the carrier frequency. When the frequency of the modulating oscillator is tuned to an audio rate above 20 Hertz, very interesting things happen to the sound. Additional frequencies called sidebands appear symmetrically around the carrier frequency. Those above the carrier frequency are called upper sidebands, and below are called lower sidebands. To create these sidebands, some of the energy of the carrier frequency is being stolen to energize these additional frequencies. So I've got two oscillators here, one producing 1,000 hertz, one producing 200 hertz. Here's what it sounds like in a additive synthesis. So we can see both frequencies. Now I'm going to change the algorithm to FM synthesis, and I'm going to slowly bring in the other oscillator and just see and hear what happens. So that's quite a difference again. FM synthesis, additive synthesis. Watch as I adjust the frequency of the modulating oscillator. So as you noticed, when the sidebands were sort of moving up and down, particularly those ones that are going down, what happens is eventually they would become negative numbers, but there's no such thing as a negative frequency. So they bounce back from zero at their absolute value, but they're 180 degrees out of phase with what their original phase would have been. If these frequencies do not bounce back on top of other frequencies, then the phase reversal is inaudible. However, when sidebands do bounce back on top of other partials, phase cancellation or summation has a great impact on the timbre. As with ordinary complex waveforms, the timbre perceived by the listener is determined not only by the frequencies present, but also by the relative strengths and in some cases their phase. So in FM synthesis, the ratio of the frequency of the modulating oscillator to the frequency of the carrier oscillator really matters. It is the ratio of the modulating frequency and the carrier frequency that has a lot to do with the quality of the sound. When we choose simple whole number ratios like 5:1, we typically get sounds that have a lot of very harmonic sounding overtones. So here are some examples of those. So here's 200 hertz and 1,000 hertz using FM synthesis. If we choose a frequency for our modulator that is not a simple whole number ratio, in other words, it doesn't divide equally into the carrier frequency, then the resulting sound will be a little bit more noisy and inharmonic. Listen to what happens as I change the frequency of the modulating oscillator to numbers that don't evenly divide into the carrier frequency. I can really get a sense of sound design if I change the envelope of both of these. So let me make this actually a much shorter sound. So now I get a much more sort of metallic bell-like or cymbal-like sound. So doing FM synthesis using just sine wave is a very traditional way to do FM synthesis. It's cool that we can take a few simple sine waves to create some incredibly complex sounds. You can imagine if we were trying to reproduce this sound in additive synthesis, you'd need to have a single oscillator producing every one of the partials that are present in this FM produced sound. Right? Every one of those harmonics would have to be its own oscillator. So what's nice about this is with FM synthesis, We only need 2 oscillators to create a huge variety of frequency-rich and varied sounds. I want to show you what happens if we start changing the waveforms instead of using just sine wave. Here is my carrier oscillator, just producing 1000 hertz with a sine wave. Let me change this to a square wave. So now you can see a number of harmonics there. So I've still got my oscillator B here set to sine wave. Let's see what happens if I start to just slowly bring up this level. So you could see a whole bunch of sidebands on either side of all of those frequencies present in the carrier oscillator. You should remember that sounds get incredibly rich really fast. So think about bringing up the level or the depth of the modular and carrier oscillators very slowly to hear the real difference in variety and spectrum of sounds. Also remember that as you add envelopes to these oscillators, we start to get a huge variety of sounds that we can create. Also remember that in Operator we have different kinds of FM algorithms up here. So as we work with 2, 3, or even 4 oscillators being modulated into one another, we might sometimes get very different sounds by how these sort of interact. So I'd encourage you to experiment with all of those. And you can also add a lot by using filters to this as well. Let's take a look at how we can apply a filter and an LFO to a pretty simple FM synth patch. So I've got one oscillator here. My first oscillator is just a sine wave. I've got a pretty low frequency of 180 hertz. And then for a second oscillator, let me bring this way down. And in fact, I'll just set this to the default rate right now. And so my other oscillator is not a nice simple ratio here, 256 hertz compared to 180 hertz. It's also producing a square 4 wave. So I'm going to slowly bring in this sound, and I'm just going to move some of these levels around to find a sound that I like. Okay, that's pretty cool. I am using 2 sort of gradual attacks here for the envelope. I'm going to add a filter to this. So I'm just going to add a high pass filter. I'm going to adjust the frequency and resonance. That sounds pretty cool. And then I'm going to add an LFO to this, and I'm just going to add some vibrato. And let me bring the rate and the amount down. Actually, I'll bring the rate up and then slowly bring the amount up. And I can play with the waveform for the LFO. Here's a sawtooth. That's pretty cool. And finally, let me actually add a sample and hold to kind of create some random melodies with this. Right, I'm just holding down one note on my keyboard. I'm just holding it down, and the LFO is basically creating a tune on its own. This is a great old analog synth technique. Check out sample and hold. and using that in an LFO. And again, our LFO is only controlling the modulating oscillator, right? I'm not having it touch the carrier at all. It's just being applied. The LFO is only being applied to B. In fact, let me try different options here. Both those are pretty cool.